Making a nuclear bomb is much more straightforward than making a nuclear reactor. A nuclear reactor is very similar to a nuclear bomb, except without the bomb bit. It's not the exploding part that adds the complexity to a nuclear reactor. There is also the question of safely using the energy generated by a nuclear reactor, which adds a bit more complexity to it as well. Firstly, we need to know how to make energy with a nuclear reactor. The principle is exactly the same as with a nuclear bomb, so you have to listen to the previous podcast first. Secondly, we need to make the nuclear reaction not go critical. A nuclear reactor has control mechanisms in place to limit the chain reaction, so it becomes a controlled reaction rather than an explosion. These control mechanisms come in two parts: the moderator and the control rods. The moderator is a material which slows down the neutrons produced in a nuclear reactor. Most often this moderator is water, as it is readily available, can fit any space, and can also be used to transport the heat of a reaction away from the reactor vessel to the power generation section. A better moderator is heavy water with deuterium rather than hydrogen in its bonds. Heavy water is more expensive than normal water, but it does mean you can use lower concentrations of uranium-235 in your fuel rods. However, the moderator can also be graphite, as this slows down the neutrons just as well. Graphite is a solid though, so it requires a different design of a nuclear reactor. It has also been involved in some nuclear reactor fires, notably Chernobyl, so you need to take a lot of care. The key aspects of any moderator is that it does not absorb many neutrons, but will slow them down by absorbing a lot of their initial kinetic energy. Water-moderated reactors have an added safety feature in that if you lose the water moderator, you also lose the nuclear reaction. The neutrons coming out of the uranium are too fast to cause the further fission events. However, losing the water also removes the ability to cool the reacting material, which can lead to an overheating and melting of the material. The next key ingredient to a nuclear reactor is the control rod. Control rods are similar to putting a wet blanket on a fire. Control rods are designed to absorb lots of neutrons and so stop a nuclear reaction. Different chemicals can do the job depending on the design of your reactor and the reaction type you are looking for. Typical control materials are silver, boron, iridium and cadmium. The design of your reactor and its maintenance is key to the successful implementation of control rods. In reactors with a vertical alignment, control rods are raised and lowered from in between the fuel rods to change the rate at which the uranium fuel reacts. If you raise the control rods, you are allowing more neutrons through to react with more uranium nuclei, and so increasing the rate and the temperature of the surrounding coolant, and therefore generating more power. If you lower the control rods, you are decreasing the rate. In a vertical alignment, it is possible to drop the control rods in an emergency to stop the reaction. If this doesn't happen, and the control rods do not fully stop the reaction, then the reactor will continue to react and give a possible explosion. This is also why the mechanisms for raising and lowering control rods need to be well maintained. If these mechanisms do not work properly, then the reactor can blow. The choice of material for control rod depends on a few criteria, not least cost and mechanical properties. If a material cannot be made to fit the shape required for a given reactor, it is useless, irrespective of how well it absorbs neutrons. If it costs so much to manufacture and maintain, then it makes an already expensive energy production method a white elephant project. One of the most important factors about the material itself is the absorption cross-section of that material. That is how easily the material absorbs neutrons of a certain type. A material that is very good at absorbing slow neutrons will be no good in a fast breeder reactor, and vice versa. The final aspect to consider in a nuclear reactor is the coolant. A coolant is a material which removes heat from the reactor core and transports it to a boiler of a power plant. This coolant has to be isolated from the boiler because it will contain radioactive particles from the nuclear reactor. In some reactors, the boiler is bypassed and the coolant is turned to steam to turn a turbine. However, this in itself has its own safety problems. You also want to reduce the chemical erosion that can be done to the nuclear components to increase the lifespan of the reactor. It needs to be a good conductor of heat, so that the reactor heat can be moved quickly and efficiently to where it's needed. Two of the most common materials to do this are water and liquid sodium. Water has the benefit of being able to moderate the nuclear reaction as well as cool it efficiently. However, it isn't the best moderator as it does absorb neutrons. Heavy water would be better, but is extremely expensive. How the water is used also depends on the type of reactor. Some reactors, as said before, allow the coolant water to be boiled within the reaction chamber, and this in turn spins the turbine to make electricity. This brings the radioactive coolant much closer to the external operations of a power plant and has inherent dangers. Another type requires the water to be kept at a very high pressure so that the water remains liquid at high temperatures. This water in turn is used to heat water in a separate loop containing the radioactive water to within the reactor vessel. The high pressure here can add an extra element of danger, but is easily controlled. Sodium is a highly reactive metal, as anyone who's seen the school demonstration can attest. If it reacts with water, it can produce hydrogen gas, which is very explosive. Also, sodium is a solid at room temperature, so it needs to be heated to become liquid and transport heat away from the reactor. However, if the sodium were to come in contact with air, it would spontaneously combust, containing a hot fire that could consume many other parts of the plant. It is the ideal choice for fast breeder reactors, but it's still very dangerous and radioactive, albeit with a short half-life once exposed to the nuclear reactor.